Okay, so here we have question 7 on shear force and bending moment diagrams of a beam with all types of loads, or section 7.1. So here the question is, Philip is playing football and is hit on his femur by two opposing players. If the shear force to one area of his femur exceeds 40 newtons, his leg will break. If the bending moment of the bone exceeds 100 Newton meters, then the muscles in his leg will tear. Using the diagram, determine what injuries Philip will obtain. So by asking the if the shear force to one area of his femur exceeds 40 newtons, that's basically asking for the absolute the maximum absolute value of shear force, and it's doing the exact same thing for bending moment. So the first thing we're going to do here is we're going to actually draw out our bone, except we're going to be looking at making it into just we're going to be looking at making it only into our external forces, and now and that's what we're going to be doing here. So first things first, we're going to have our I'm just going to use a rectangle because it's just a little easier to draw here. So we're going to be doing a reaction at point A, so R sub A, and there's technically two reaction points at B, R sub B. However, I'll explain why it actually ends up only being vertical. So the whole reasoning behind why it's just vertical is because technically I do need a B sub x going in this direction, and it's going to be the only horizontal force, which means that when I do sigma F sub x equals 0, all I'm going to get is B sub x equals 0. So therefore I can kind of just ignore B sub x. So now that I have my R sub A and R sub B right now, I'm going to start, I'm going to get my forces coming down for my 10 Newton and my 4 Newton. So when I have a 10 Newton force listed like this, it's basically saying the height of this shape is 10 Newtons. So the height here is basically saying that there's 10 Newtons, and it's over a 5-meter spread. So if I do 10, so in order to get my force caused at one point when I have a distributed load of a rectangle at that, I do 10, I do my height times my base to figure out the total amount of force created by this distributed load, 10 times 5. And this all equals 50 newtons between the whole distributed load. Now, when I actually go to this, now what I'm going to do is I'm going to try to figure out where that force is coming down. Now, because it's a rectangle, it's just going to be coming down from its centroid, or the center of it. So that means it's just going to be 5 divided by 2, which then equals 2.5 meters. So that means that it's going to occur about midway between point A and point B. So that tells me here to there is 2.5 meters. So given this, that tells me that I'm going to have a force coming down here of 50 newtons. Now we're going to be doing the exact same thing for the 4 Newton part. So that means I'm going to be taking my force of 4 newtons, I'm going to be multiplying it by its width. And its width here also happens to be 4. This equals 16 newtons. So I'm going to do the same thing here because it's going to be coming down from its centroid. However, if you remember, we're going to do our 4 divided by 2, but we have to add the 5 because it doesn't occur directly at the end of the bone near point A. So it's going to be 4 divided by 2 plus 5. This equals 7 meters. It equals 7 meters. So that tells me that this distance from, I'm going to just use, because we know here is 5, the distance from there to there is 5. And that tells for the additional 7, I can just grab that from B and go an additional 2 meters away from B. Now, and that's where my force of 16 newtons will be coming down. Now we're going to try to solve for our reaction at point A as well as our reaction at point B. So first thing we can do for that is we can use another equilibrium equation we have in the y direction. So this should equal 0. So in doing this, I'm going to start off with my positive values. So my two positive values when I'm doing a force in the y direction is r sub a plus r sub b, and now I'm going to subtract my my forces in the downward direction. So that's going to be minus 50 minus 16, and this all equals 0. So now I'm going to simplify this out and get r sub a plus r sub b minus 66 equals 0. Now I'm going to add 66 to the other side, which then gets me r sub a plus r sub b equals 66. So now we're going to have to try to solve for either r sub a or r sub b. Now when I look at this, my immediate thought is to go into a moment, because if I use moment, I'm going to be able to get rid of one of my unknowns. So that tells me I can do a moment at either point A or point B. I'm going to choose point A because it then keeps all my forces on one side. However, you can also do it with point B. So I'm going to do sigma of moment at point A equals 0. So when I do this, I'm going to start off with my positive values, or the forces that move in a counterclockwise direction. So when I do this, I'm going to get 5RB because it's 5 meters away from point A, and now becomes our negative values. So I'm going to subtract 50 because that's one of that's force that we have. However, we know that to be 2.5 meters away. So minus 2.5 times 50 times 2.5. Now I'm going to also subtract our 16 Newton force, and I'm going to multiply it by its distance, which we determined earlier to be 7. So times 7, and this equals 0. Now when I multiply this out, I'm actually going to get 5r sub b equals 237. Because it's a negative value, so I also added it over to the other side. And when I do that, I get r sub b equals approximately. Now I'm going to now when I actually do this problem, I'm going to use the exact value I get here. However, I'm just going to write out, I'm just going to simplify it a little bit, so that way it's a little easier for me to write and it takes less time. So I'm going to get equals approximately 47.4. So now I'm going to plug that in and try to solve for my r sub a. So when I do that, I'm going to do r sub a plus 47.4 equals 66. So using this equation, I'm going to get r sub a, because I'm going to r sub a equals 18.6. So now I'm going to be moving on and trying to solve my shear force. Now there's multiple ways of doing shear force. You have one way that takes a while, however, and then you have the faster way. So I'm going to be doing the faster way to solve them. So now the point at r sub a that's creating a force from a singular point, which means it's going to jump. It's going to jump by the force that's created there. So that tells me that when I go to create my shear force graph, when I go to create that, it's going to start off by going up to 18.6. Now what I'm going to do is I'm actually going to take that 18.6 that I have there, and I'm going to subtract 50 from it. So I'm going to do my 18.6, and I'm going to subtract 30, sorry, not 30, 50. And when I do that, I'm going to get negative 31.4. So that tells me that it's going to ultimately go down to 31.4. However, if you remember, this is not a this here is not a singular point creating a force. It's actually a distributed load. So that tells me that it's not going to create that instantaneous jump to the next value. It's actually going to create a slope that leads there. So when I do this, I'm going to get it's going to ultimately go down to negative 31.4, but that's going to occur at, say, 5, at about 5. So we're going to put 5 right there on the graph. Now we're also going to put 9 here. And because those are our two big, those are our two, like that's 9 is our end of the beam, and 5 is where we have, is where the force of 10 newtons, the distributed load of 10 newtons ends. So that tells me here that this is going to go down until it hits negative 31.4 down here, which then gives me a slope, because it's a distributed load, between those two. Now, we're looking back. Now we have here at 5 newtons, we also have a force of our reaction force B, which we figured out before to be 47.4 back up here. So what we're going to do is we're going to actually add our force. Now keep in mind, this isn't a distributed load anymore. It's a force coming from a singular point. And as a result, it's actually going to create us our jump again. So what I'm going to do is I'm going to take our negative 31.4 and I'm going to add 47.4 to it. And when I do this, I end up getting 16. So that here is 16. Now I'm going to worry about solving out for our next force. And our next force here is actually going to be that distributed load that was 4 newtons up top, right here. So given this, we know that it's spread out over 4 meters, which is going to bring us to 9. And we know it ultimately has that force of 16 that we solved. So that means it's going to create that change by 16 newtons. So I'm going to do 16 minus 16, and when I do that out, I'll get 0. So that tells me that our bending moment ends right there, back at 0. So if you remember though, with the equation, it was asking if our force ever exceeds 40 newtons. If our force ever exceeds 40. So as a result, when we go to do this, we're going to be looking at this, and we look to see if our force the absolute value of our force ever exceeds 40 newtons. Now, the highest force we end up getting is actually this negative 31.4 value, because that ends up being our highest force. So if I take an absolute value of that, I'm actually going to get 31.4. And now 31.4 is less than 40, which tells me that Philip's leg does not break. So far he has sustained 0 injuries after our shear force. So what we're going to start working on now is we're going to start working on our bending moment. Now, a way that you can solve bending moment is through areas. So I can use the area under my shear force diagram to get my bending moment diagram. So as a result, I'm going to, but in order to do this first, I have to figure out where this point is. The point there where that equals 0 between 18.6 and 31.4. So the way that we can do this actually is solving for slope. So slope is rise of a run, so change in y divided by change in x. So I can do my negative 31.4 minus 18.6 divided by, because my change in x was over the course of 5 meters, 5 minus 0. When I do this out, I'm going to get negative 50 over 5, which ultimately equals negative 10 newtons per meter. So now I can use this to actually solve for my where it equals 0 by plugging it into the equation y equals mx plus b, because I already know my m, so y equals negative 10, because that is my slope, x plus b. B is my y-intercept, which is 18.6 here. So now I'm going to be solving for when my y-intercept equals 0. So that actually tells me I do 0 equals negative 10x, because we don't know it, plus 18.6. So what we're going to do is we're going to add our 10 to the other side, which then tells us that 10x equals 18.6. So when we divide this, we get x equals 1.86 meters. So that is where our shear force diagram equals 0. So now when we go to solve this out, we're going to be using the area under the curve. Or in this case, under the diagram where we have triangles. So the area of a triangle is 1/2 base times height. So we now established that this here is 1.86. So that tells me our first triangle, so I'm gonna color it blue, is here and goes from a height of 18.6 and has a base of 1.86, and of course now I have to multiply it by 1/2, so times 0.5, and this, when I do this out, I'll end up getting 17.298 Newton meters. Now that we have that, we can move on to our next triangle. And the way that we do this is we actually aren't going to be adding our values up. Like our value is not going to be based off of our previous. So I colored the triangle in that we're going to be doing now in green. So the first thing we have to do is we now need to figure out how long its base is. So we established that it equals 0 at 1.86. So that tells me in order to figure out the base of this triangle, I have to do 5 minus 1.86. And when I do this out, I'm actually going to get 3.14 meters. So that tells me its base is going to be 3.14 meters long. And it has a height that we know to be negative 31.4 times the length of our base, which is 3.14 times 0.5. And when we do this out, we're actually going to get negative 98.596 Newton meters. So now we have two of 3 triangles solved. So now we have to do this very last triangle right here, which I'm going to color in purple. So now when we do this out, we're going to get, we already know its base is going to be 4. And we know its height is going to be 16. So this one's actually fairly simple. It's 16 times 4 times 0.5, which if you do out, gives you 32 Newton meters. Now, this question was asking if the Newton meters ever exceeded 100. Now, so that tells me that here I can do my absolute value of my highest point between these three, which happens to be negative 98.596. And here, when I take an absolute value of that, I'm going to end up getting 98.596, which is, albeit not by much, less than 100. So because that is less than 100, that tells me that here, Philip's muscle does not tear. Philip's muscle does not tear. Which then ultimately tells me, because his leg does not break and his muscle does not tear, that Philip sustains no injury in this tackle. And therefore, that is my answer to this question. Philip sustains no injury in this tackle. Thank you.